All right, we are good to go. Okay, so a couple announcements that I had for you today. Remember that your quiz is due today at 5 o'clock. And if you haven't had an opportunity to really learn about hearing and stuff like that, we are going to talk about that today. And also, I'm planning on finishing up sensation and perception today. Hopefully you noticed that I also have notes up for learning and conditioning, which is what we are going to be covering next. I received emails from many of you about your project ideas. For those of you that are working alone, and I know there's a few of you, so one of the things that we're going to do is, for those of you that are working in groups, 20% of your grade comes from how well you worked together. So I'm going to give you a rating form after you turn in your project where you have to rate how the rest of your group kind of did. So that way, if it turns out that somebody's not pulling their weight, everybody gets an opportunity to kind of rate themselves and rate their group mates. And I'll kind of get a pretty good idea of how much you contributed to the project. Thankfully, because I am letting you work with people that you want to work with, there shouldn't really be a lot of problems with that. Hopefully you get along with people in your group. Now, if you're working alone, I obviously can't have you rate how well you got along with yourself. If you aren't getting along with yourself, you've got bigger problems than the project. But what I am going to have you do if you are working alone is what I would like you to do is I want you to do a self-assessment. So in about one page, I want you to tell me how you thought you did on the project, what sort of things worked for you, what sort of things didn't work for you. And now that you have the final project in front of you, what worked, what didn't work, what would you have done differently? So I will expect a little bit more thought than a simple 1 through 3 rating. That the people who are working in groups get to do. I hope that's okay. Any questions on the project or anything like that? Remember that it is due, if I am not mistaken, November 15th. All right, great. So let's continue our discussion of hearing. And I didn't want to delve too far into it. If you haven't watched the video that I recorded for you to watch on Friday, please make sure that you watch it so you can learn more about visual perception and color constancy, and you get to see some really cool illusions, which I thought were great. But we're going to move on to hearing. So as I mentioned at the very end of the lecture that I recorded for you, one of the things that sensation always does is it converts physical energy into a stimulus that the brain can actually use. And hearing does have, or vision does have a tendency to kind of dominate these things, but hearing is probably our second most important sense. So hearing comes from the physical stimulus energy of sound waves. So as you speak, your vocal cords vibrate. And yes, technically they are called vocal folds, not vocal cords, but I'm going to go ahead and call them vocal cords because I feel like you all know what those are. Your vocal cords will kind of vibrate. So go ahead right now, put your hand up to your larynx, right around your neck, and just go, mm. Can you feel it vibrate? Now, there are some sounds that you make that do not vibrate, but most of the time, when you push air through your lungs to speak, that causes vibrations in your vocal folds, and that will cause changes in sound pressure waves, and that's what allows you to hear. So what's really critical for sound is that molecular collisions have to happen. Air molecules actually have to move. It's part of the reason why there's that saying in space, no one can hear you scream. Yes, that's a tagline from Alien, which is an amazing movie. And I would recommend that if you're trying to watch Halloween horror movies, Alien is basically a haunted house movie, but in space. But sound can only be heard when we have those molecular collisions. Space is a vacuum. And that's why you generally are not able to hear anything in space. If you were actually able to take off your helmet and breathe, which you are not. But how many of you have kind of had this happen where you can't really hear on your phone and you've got your speakers up, but you put it against a wall or a corner of a room and all of a sudden you can hear it better? When you put it up against a corner, you have more opportunities for those air molecules to collide. And that's how you end up hearing things. So when we look at a sound wave, it's going to have the characteristic of a sine wave. And so generally, when we look at a waveform like this, we have two things to think about. We have our amplitude, which is how high the wave actually gets, where is its peak. And then we have frequency, which is how many alternations of this up and down cycle do we have for a set period of time. So as I finished up class, the recording on Friday, amplitude, that peak, the height of that peak, corresponds to our perception of loudness. And then frequency, how many cycles you have per second, corresponds to our perception of pitch. So while some of you are taking these notes, I have a question for you. So how many of you, when you were growing up, played Marco Polo? Okay, so how many of you have seen this happen where you're in the pool playing Marco Polo and you duck your head underwater and you hear sound, but what do the sounds sound like when you're underwater? Kind of hard to hear, isn't it? So one of the things that we know is that when you go from one medium to another, such as when you go from air into liquid or fluid, sound loses some of that energy. So it's kind of why if you stick your head underwater in the pool and you hear somebody talking to you, it's going to be dampened, because as that sound wave moves from air into water, it loses some of that energy. Now you might be wondering why I'm talking about this. The reason that I'm talking about this is in just a second, I'm going to talk to you about how the ear works. And one of the things we have to talk about is how do we keep sounds from losing their quality when we go from air into fluid? Because as it turns out, some of the structures inside of our ears, they're fluid. How are we able to hear without losing that sound quality? So this is your ear. So I know that it's really easy to think of just these as your ears, but really the parts of your ear go far deeper inside of your head than you would expect. So first of all, go ahead, hold on to those little fleshy ears and give them a wiggle. These are what we call our outer ear. This is what is called the pinna. Now, if you feel around inside of your pinna, so I'm going to kind of look up to the screen. One of the things that you'll see is that your pinna has different types of grooves and enclosures and things like that. And if you look around the room at your classmates, you'll probably notice that many of you have different pinna. Everybody's pinna is a little bit different. But this basically serves to act as a funnel. It helps you localize sounds. So all of these grooves help you figure out where sounds are. And they also are going to be critical for funneling sound into your ear canal. So now we're in the ear canal. And contrary to what this picture looks like, the ear canal is very, very short. And it ends with this little membrane right here. This is sometimes called the eardrum, or if you want to be more technical, And because Zoom's working right now, I can show you. Another name for the eardrum is the tympanic membrane. The tympanic membrane. So when you think about it, it kind of works like a timpani. A timpani is a type of drum. So the eardrum is a thin membrane. It's made up of skin. And as sounds are funneled into your pinna and your ear canal, those sound waves will cause your eardrum to vibrate. Now, has anybody here ever ruptured their eardrum? You can actually do that in a couple of different ways. So first of all, it's part of the reason why they tell you not to stick Q-tips in your ears for cleaning. Yeah, you're not supposed to do that, but I'm not gonna lie to you, I do. My ears get itchy. My ears get very itchy, but it's why you're not supposed to stick anything in your ear canal, because it can actually puncture the eardrum. Or what's probably more common is that if you have a cold or you have nasal congestion while you're flying, those changes in pressure from takeoff and cruising altitude and touchdown, those changes in pressure can actually cause your eardrum to rupture. Now, your eardrum is just skin, so it's able to heal itself. But the sensation of a rupturing eardrum, I have been told by others, is very unpleasant. So take good care of your ears. Don't stick anything inside them that you would, could potentially hurt you. Okay, let me go ahead and get rid of tympanic membrane. So sound waves go through the ear canal and they cause the eardrum to vibrate back and forth with those sounds. Just behind our eardrum, we have 3 tiny bones. So we have these 3 tiny bones, and I'm going to go ahead and pull up annotate again. I'm going to put it right over here. So sometimes these tiny bones are what are referred to as the ossicles. Ossicle is another word for bone. So our 3 bones are the malleus, which is sometimes called the hammer, the incus, which is sometimes called the anvil, and then the stapes, which is also called the stirrup. Guess why we call them all of these things? Because that's what they actually look like. So here's our hammer. The hammer goes directly to the anvil, which is right here, and then you have the stirrup right here. And it actually does look like a stirrup that you could put your foot in, whether it's on a bike or a horse saddle or something like that. So what do each of these bones do? So remember how I talked about the fact that when sound goes from air into liquid, it loses its quality? Here's something interesting. So our inner ear is right here. It's this little snail-shaped organ called the cochlea, and it's filled with fluid. So far, our sound waves have been traveling through air, and they're going to have to be transferred to an organ that's filled with fluid. We don't actually want our sound to lose quality as that transfer happens. So what do? The bones of the middle ear, so our hammer, our anvil, and our stirrup, as the eardrum moves, are going to pump back and forth like a piston. So they're going to pump and amplify that sound. As they amplify that sound, notice that the stirrup is directly attached to the cochlea. That's going to cause the fluid inside of the cochlea to move. And because those tiny little bones are there, they amplify the sound so that it doesn't lose quality when it hits that inner ear. So these tiny little bones help amplify sound so they don't lose quality. Now, finally, we have the cochlea of the inner ear, and I'm mostly going to focus on this. Now, this is all bone. So in each ear, you've got a little bony snail shell. Yeah, your ears are weird. I'll just say it. Additionally, one thing that you will kind of notice is that there are these 3 little tubes directly attached to the cochlea. Those you don't need to worry about. I'm not going to test you on them. Those are, I think your quiz might though. Those are your semicircular canals. They help you figure out your position of your body in space and how you rotate. So if you've ever been on like the spinning teacup ride at Disney and you've gotten really dizzy from all of the spinning or on other rides, it's because of the semicircular canals. But we're largely going to focus on the cochlea for hearing. So inside of the cochlea, we have our sensory receptors for hearing. They're called hair cells because they each have a little hair sticking out. And as the sound wave, so as the sound wave moves, so remember we started with vibrations in the eardrum, that transfers to the bones, which pump back and forth. That causes the fluid in the cochlea to move, and inside that causes the hair cells to move back and forth as well. And it's that moving back and forth of the hair cells that helps us figure out aspects related to sound, including frequency and loud or pitch and loudness and location. So here's something that you need to know about your hair cells. Your hair cells, like the rods and cones in your eye, are special neurons. If you damage them, neurons don't grow back. So if you damage your hair cells, they do not get better. So one of the things that we know that destroys hair cells pretty easily, exposure to loud noises. And that's especially going to hurt higher frequencies because higher frequencies are the first thing that the hair cells that code for higher frequencies are right at the opening of the cochlea. Deeper sounds tend to be closer to the little inner portion of the cochlea, and thus when you get older and the hair cells are damaged, you actually lose your ability to hear high frequencies. So it's part of the reason why, as my grandmother got older and her hearing declined, she probably had a harder time hearing my voice than she did my dad's. I have a higher pitch voice than my dad's. Higher pitches are going to be harder for you to hear as you get older. So I'm going to stop share for a minute because I'd like us to do a test, and I'm going to embarrass myself. Now we're doing this on a projector and through a speaker system. Honestly, the best way for this to work is with headphones. So feel free to try it on your own time, but I'm going to embarrass myself and show you how old my ears are, and you can also test how old your ears are too. We're going to pause share for a minute. Okay. And Chrome. You know how I feel about Microsoft Edge. Okay. Okay, are we ready? Okay.
As we grow older, we often lose the treatments of our hearing spectrum. So, how many of the following?
Raise your hand if you hear it.
How old are your ears? Okay, if you can hear 8,000 hertz, you're both alive and not hearing impaired. But let's keep raising the frequency.
Yeah, I can't hear that.
I don't want that.
I'm sorry. Some of you have very good ears that you've not destroyed with headphones. It got caught on you saying, I don't want that.
If you can hear all of those frequencies, you're probably under 20 years old, but that will last forever.
No, it won't.
Such as the liver or skin, the inner ear does not have the capacity to regenerate. In your ear, there are thousands of tiny nerve cells called hair cells. These are responsible for picking up different frequencies and sending the signal to the brain where it's processed. But as you age, the continual exposure to noise and loud sounds can break, bend, and destroy these cells. So why do the high frequencies go first?
box there at the
It
end.
turns out that the hairs tuned to high pitches are the first to encounter sound waves.
Yep.
As a result, they experience more stress and tend to degenerate earlier, which is why the older you are, the harder it is to hear high pitches. Got a burning question you want answered? Ask it in the comments or on Facebook and Twitter, and subscribe for more weekly science videos.
So one of the things that I think is kind of interesting that was kind of popular when, oh, I got fuzz in my mask. One of the things that I thought was kind of interesting is that in general, the younger you are, the higher the pitches that you can hear. You've had less opportunity to encounter loud noises, and because of that, your hair cells are pretty much intact. Also, unlike me, you probably haven't had the chance to destroy them with years and years of listening to things on your headphones because you like having a personal soundtrack. Yeah, to my own detriment. But what I thought was kind of interesting is that, especially in the early 2000s, it was really common to have, like, the mall was still a really cool place to hang out. And so at least before curfews started being put in place to keep teenagers out of the mall without a parent or a guardian at certain points, because sometimes roving groups of teenagers like to start fights. Yeah, I don't get it. I just wanted to go to the bookstore when I was a teenager. I guess I don't get it. But they would play these high-pitched sounds that only the teenagers could hear, and the adults around them couldn't, and that would get them to leave. What was interesting is that a couple of years later, I remember seeing advertisements on TV about the special ringtone that you could get for your phone that no adult could hear. So they basically took that technology that was basically being used to drive off teenagers to be like, teenagers are cool. We can still hear. Your parents won't be able to hear this ringtone. You know, I just thought it was kind of a weird bit of marketing. But anyway, okay. So all of the sound that is going on in your outer ear, middle ear, and your inner ear code for things like pitch and loudness, and also the complexity of sound. But when we talk about locating sound, that is not something that the inner ear actually does for us. This is something that our brainstem actually does for us. Now, one of the things that's very helpful about your ears is that they are 180 degrees apart from each other. That makes localizing sounds very, very easy. So the distance between our ears actually helps us locate sounds. We can look at differences in intensity. So if somebody is over trying to talk to me on this side of my ear, it's going to be louder in this ear than in this ear, because it's going to have to travel around my head to get to the other ear. Now, likewise, if the person is talking to me over here, it will hit this ear before it hits this ear. So our brain can actually calculate intensity differences and timing differences to help us locate sounds. So we can use those differences to figure it out. Now, unfortunately, because I am recording, I can't really do this demonstration for you because I have to stay right here in front of the camera. But one of the things that we can find, and you can try this with a friend later, snap in different locations and have your friend try to point to where they think the sound is coming from. And then at some point, try to get it at the center of the head. They're going to have a very hard time figuring out where that sound is coming from, because as you get closer to the center of the head, it hits both ears with equal timing and with equal intensity. And thus it makes it harder for us to figure out the location. So some sounds that have a clear left or right side are easy for us to locate. Sounds that are kind of in the center of our head are harder for us to locate. always nice to see bucket hats making a comeback too. Like sweater vests and bucket hats. I wish I was more of a hat person. Like I'm only a hat person when it's cold, and that's more by necessity. But I always wanted to be that person that wore cool hats. And I'm just like, I buy hats and then I never wear them. Okay, everybody good? Okay, let's briefly talk a little bit about touch, taste, and smell. So one of the things that's kind of interesting is that touch actually codes for different types of sensations. So whereas our rods and cones code for one sense, vision, and here our hair cells code for hearing, touch is a little bit different because touch codes for a variety of sensations. So that includes pressure, such as, I actually had somebody shake my hand yesterday, and I haven't had anybody shake my hand in like a year and a half. It's actually kind of amazing. But how many of you have had this happen where you shake somebody's hand and it's almost like they're going to take your hand off? Thanks to the receptors that are embedded throughout your skin, you can actually code for pressure. We also need pressure when we're reaching or grasping for things. So we have receptors in our skin that can actually detect how our skin stretches so that we can figure out if something is slipping from our grasp or how to tighten up our grasp to hold on to things. So we have very specific receptors embedded throughout our skin that code for pressure. We also have specific receptors in our skin that code for temperature, both warm and cold. So you don't need to write this down. The pressure ones are called mechanoreceptors. We have the ones for temperature. Those are called thermoreceptors. Interestingly enough, I actually just read that the Nobel Prize in Medicine was awarded today to people who actually did research on thermoreceptors and temperature like perception in skin. And I thought that was pretty cool. And then we also code for pain. I don't know if you can see this. I burned my hand on my hair straightener. So my pain receptors were working overtime there. And the receptors that are responsible for pain are what are known as nociceptors. So we actually have all of these different types of receptors embedded throughout our skin. They not only respond to pain from burns and cuts, but they can also respond to pain from chemical burn, and also some of these are actually embedded near your visceral organs. So if you are having a stomach ache or you ate too much food and you're very full and it feels painful, the nociceptors near your visceral organs can code for that as well. So these are some of the basic sensations that we get through touch. So let's talk about pain. And I'm not talking about emotional pain, although that is a very different sort of pain. Pain, physical pain, is actually essential for our survival. Nobody wants to hear that, but it's true. Think about it this way. If we never felt pain, our ancestors would have been like, hey, let's go see if we can pet that rattlesnake. And we never learn that that's a bad thing for us to do. Our ancestors might have said, hey, that cliff looks really high. Let's jump off of it and see what happens. And we never realize that that's not something we're supposed to do. So pain gives our body a sense of warning that something that we might be doing is deadly or even just dangerous. Additionally, in our everyday life, most of us will not jump off cliffs for the heck of it or try to pet a rattlesnake for the heck of it, but we might engage in a lot of physical activity. And sometimes when you strain something too hard, when you're working too hard and not really getting an opportunity to recover, That's your body's message that it's time to rest and recover. So pain is really critical in that it makes sure that you don't overuse your body. Now, what's interesting about pain? Now, unlike vision, which is primarily processed in the occipital lobe, and hearing, which is largely processed in the temporal lobes, there is no one specific brain region that codes for pain. There are no specific receptors. Now, yes, we do have our nociceptors, but beyond that, we do not have specific receptors for pain. And pain, physical pain, can be triggered by several different types of stimuli. You can feel pain from a cut. You can feel pain from overusing a muscle. You can feel pain from touching something that's too hot. You can have pain from touching something that is too cold. You can have pain from chopping up a jalapeno and getting juice on your hands. So there are a lot of different ways that we can have physical pain triggered for us. Now, here's what's kind of interesting. We do not generally remember the entire duration of pain. We tend to remember when it starts, and we tend to remember when it ends. We have a pretty good idea of how long the pain lasted, but we don't remember the entire duration of it. So think about it this way. Have any of you talked to your parents about what happened on the day that you were born? Odds are pretty good that your mother probably was in labor for a little while, and that was pretty painful. In the case of my mother, she was in labor for over 24 hours. My dad gave her this little plush pink and white clown to look at as kind of a focus object. And my dad said, "How are you doing?" And my mom said, "I'm going to kill that clown." And my mom would never normally say that. My mom is like a very kind-hearted person. So you know this was serious. But if she remembered the entire 24 hours of pain, she would probably never want to give birth again. So our brain, especially when it comes to labor, we're actually really good at forgetting the entire duration. We know how bad it felt when it was at its worst. So we remember the peak, we remember what it felt like when it started, and we remember what it felt like when it ended, but we do not remember. In the case of my mom, she does not remember what it felt like for a full 24 hours. So we remember the peak of pain. We remember how much we felt at the end. We know how long it lasted, but we don't remember how it felt for the entire duration. If that were the case, nobody would ever want to have a child again because it would just be too painful. So that's actually kind of interesting. Has anybody here ever broken an arm or a leg? Okay, Lily, how did it feel? You don't remember? Do you remember, like, in your mind, maybe how it felt at first?
I don't remember anything.
Okay. Okay. Gracie, I saw you raise your hand too. Is that kind of the same experience for you?
Yeah, the initial pain I remember really well.
Yeah. So we remember how it felt at its worst. We tend to remember how much we feel at the end, but not much about the duration of it. And that's probably a good thing, because otherwise we'd probably end up like SpongeBob, staying inside with his friends. The penny, the tissue, wasn't it the rock? It was a tissue, a penny, a tissue, and what? And singing about being indoors because you'll never get harmed. A magical place with magical charms. I won't sing it. You deserve better. But I bet you're thinking it. All right, does anybody need some more time here? Okay. Good. Okay. Oh, wait, that's not what we wanted. Taste. Taste is one of my favorite senses, and that's just because I like food. So one of the things that I kind of want to share that we'll talk about more probably next spring, if you're interested in taking sensation and perception with me, is how many of you remember seeing like a tongue map where it was kind of like the sweet taste was at the tip of the tongue and the salty taste was on the sides? Well, it turns out that that tongue map was a lie. It was mistranslated from German. And people believed that different parts of the tongue code for different types of tastes, but that's not true. And odds are pretty good if you're like me and you saw something like that, you'd suddenly try to put like a lemon on the tip of your tongue and see if you could taste it. It turns out that you can. And that's because there is no one part of your tongue that codes for one specific taste. Your tongue codes for all of the tastes. So let's talk a little bit about how taste works. So unlike touch, unlike vision, and unlike hearing, taste is a chemical sense. It is critical for chemicals to actually come into contact with the taste receptor cells in your tongue. Now, what you're looking at here is a taste bud. So this is the receptor cell, the supporting cell that supports your sense of taste. Now, if you look at your tongue, you probably notice that there are little bumps. Those bumps are not your taste buds. The taste buds are actually located within those bumps. So these little bumps are what are called papilla. And within your papilla, we actually have many different taste buds. So chemicals will make contact with this part called the taste pore. You don't need to write this down. We're not going to spend a lot of time talking about how taste buds work. So a chemical makes contact with the taste pore. This is sent to a gustatory, meaning taste receptor cell, and then that is sent to your cranial nerves, which process your sense of taste and send that information to the brainstem and then the cortex. But let's talk a little bit about some of our different tastes that we have. So many of you are probably familiar with the 4 major tastes. It turns out we might have 5, but we have sweet, and we actually have an inborn preference for sweet things. We have salty, which helps us detect things like sodium because your body needs sodium to survive. We have sour taste, which helps us detect acids because oftentimes sour taste comes from acid of some kind. And then we have bitter. Does anybody here like black coffee? Yeah, I don't. That is a very, very bitter taste. Odds are pretty good. Is there anybody here that has tried tonic water? Okay, do you like tonic water? It depends. Has anybody had tonic water? It's kind of bitter. The reason that it's bitter is that it contains a chemical called quinine. Quinine is a very, very bitter substance. Fun fact, it actually got used to treat malaria, but you'd have to drink a ridiculous amount of tonic water to basically fight off malaria. Like in that case, you're going to want medication for that and not to drink tonic water. The other thing is that tonic water, the quinine is so bitter that they usually have to put a high amount of sugar in the tonic water so that you don't notice that bitter taste. I bring in tonic water for my sensation and perception students to taste. They hate it. I love it, and so I just take the rest with me.
I like mixing it with things that like straight,
It-
it's kind of.
It's not as sweet as ginger ale, and that's why I like it. So we do have a bitter taste. That's usually used for detecting poisons. Having said that, though, bitterness is also detected in vegetables, and vegetables are not poison. But you've probably never heard of what is sometimes referred to as your 5th sense of taste. This is what is called umami. Umami is involved in the detection of things like monosodium glutamate, which is not actually dangerous for you, but some people do have a sensitivity to it. It's part of the reason why if you go to a lot of Chinese restaurants or Asian food restaurants, they will tell you there's no MSG in their food because some people do have a sensitivity to it. But if you'd like to experience what umami tastes like, it often tends to be kind of an earthier, almost meaty kind of taste. So you can detect it in things like fresh chicken. For those who do not eat chicken, mushrooms also have a bit of umami as well. Now, a lot of people debate whether or not this is actually a fifth taste. So if you want to read more or learn more about it, just let me know. So one of the things that's kind of interesting about taste is that, like a lot of our other senses, our senses absolutely influence each other. And it turns out that our sense of taste is very directly impacted by smell. So when you open your mouth to eat food and you breathe in, some of the molecules from that food are actually going to reach your nasal cavity. And it turns out that your sense of flavor is not just impacted by the taste of food, but also the smell of food. This is where I would like to remind you that if you don't make the mistake that I first made with cooking, if chicken smells bad when you take it out of the packaging, cooking will not make it better. If anything, cooking will make the smell worse, and definitely do not eat that chicken. I thankfully did not eat the chicken, but I thought, oh, if I cook it, it'll make the bad smell go away. It didn't, and it definitely didn't make me want to eat it. Like in general, if food smells bad, you're going to be less likely to want to eat it. And it also explains why if you have something like a cold or a sinus infection or allergies, when you're very severely congested, it might be hard for you to actually taste that food. One of the things that we're seeing with COVID-19, for those people that if the virus gets into the nasal passages, it can actually affect the cells that code for smell. And I actually know of some people who have had difficulty, my niece actually is still having difficulty tasting food. And that's a real shame because she loves to cook. She wants to be a chef. So I'm hopeful she gets her sense of smell back soon, and taste for that matter. Now, your expectations also will play a role. So there's a really famous study that came out, and I think your book talks about it. They had food at a dining hall, and I want to be clear, these were egg rolls that contained meat. But some students were told that the egg rolls were vegetarian, and some were told that they had meat. They're the exact same egg roll. The only thing that we have done is changed the labeling. We either told people it was vegetarian or it contained meat. Do you think the students rated how the egg rolls tasted differently? Yeah. What do you think happened? So which one do you think they rated worse? Right. So what we find is when people are told that an egg roll that is exactly the same as the other egg roll, so remember, all of the egg rolls contain meat, but the ones who were told that they were vegetarian liked theirs less. We have expectations that if it is vegetarian or vegan, that it must not taste as good as the real deal. I actually kind of see this with my partner. I will give him a cookie or a piece of banana bread and he'll eat it and he'll go, that's really good. And I'd go, it's vegan. And he goes, oh, I like it less. So we have these expectations, and our expectations influence how we taste something. So for example, did anybody ever try to make green eggs and ham as a kid? They made green eggs and ham for me in Girl Scouts once. So you get these green eggs and ham. I don't know about you, but I didn't want to eat green eggs and ham. They won't taste as good just because they don't look like how I expect. We also had this weird time in the early 2000s where ketchup was blue, and that just shouldn't be. I'll show you pictures after class. This was a thing that happened. So really quick, then we have our sense of smell. So you can kind of see how this works. So smell, out of all of our senses, is the only one that does not go to the thalamus. And again, like taste, this is a chemical sense. And you can kind of see from this picture why taste or smell influences taste. Your nasal cavity kind of goes in two different directions. In one direction towards your brain, the other kind of towards your oral cavity. So when you smell, molecules called odorants, you don't need to write that down, molecules called odorants make contact with receptor cells right here in your olfactory membrane at the top of your nasal cavity. They'll make contact with the olfactory bulb. Yes, that's what it's called. So smell has a couple of major functions. First of all, it has a relationship to food. Our sense of flavor in a food is influenced by taste because every time we open our mouth to eat or to chew, some of those molecules of smell will get into our nasal cavity. Additionally, smell warns us about dangerous food. Don't drink the sour milk. Don't eat the nasty chicken. Like, learn from my mistakes. If the chicken smells bad, just throw it away. Don't try to cook it. And additionally, one of the things that we don't quite understand about smell is that it brings up a lot of memories associated with emotions. So my mother has a perfume that she hasn't worn in years, but if somebody else around me wears it, all of a sudden I get a memory of my mom wearing it. And that's really neat. So folks, I'm pretty sure this is all I had for sensation and perception. So make sure to read through chapter 5. I will upload audio from the previous edition of the book to help you out as well this afternoon. But we're going to start learning and conditioning. We're going to watch rats playing basketball next time. They trained rats to play basketball, and it is amazing. Have a great day, everybody. I will send you a link to this video soon, and I will see you on Wednesday. Oh, I thought it didn't freeze, and it did. Oh.